Imagine the edge of a continent is like a beach leading into the ocean. Now, we're going to look at what happens as we travel from the shore into the deep, dark ocean. Good morning, good afternoon, good evening, and good day, everyone. In this session, we will discuss deep marine environment. I am Maria Grace Visipilio, and with me are Mr. Chavez and Mr. Philip, and we will be guiding you through a detailed discussion of this topic.
Good day, everyone. I'm Virgie M. Chavez, one of the reporter, and we will now talk about the deep ocean basins. The deep ocean basins cover about 71% of Earth's surface and are made of basaltic oceanic crust formed at mid-ocean ridges, where new crust is created by magma solidifying into dikes and erupting as basaltic lava are forming pillow-like shapes. These spreading centers usually lie 2,000 to 2,500 meters below sea level. As the new crust moves away, it cools, contracts, and becomes denser, causing older crust to sink deeper into the ocean. This explains why water depths increase from around 2,000 meters near the ridge to 4,500 meters where the crust is several tens of millions of years old. Take note that sediments in ocean basins are come mainly from the remains of marine plants and animals as well as dust blown into the atmosphere, collectively forming oceanic deposits. The large sediment systems are found near ocean basin margins and extend far onto the basin floor. But studying this deep water environment is difficult because so most knowledge is gained through remote sensing methods like bathymetric mapping and side-scan sonar. The next one is we will talk about the morphology of ocean basins. Continental slope descends steeply from the edge of the continental shelf at about 2,000 meters depth down to deep ocean floor at depths of 4,000 to 5,000 meters, typically with angles between 2 and 10 degrees, often extending up to 100 kilometers. These slopes are frequently cut by submarine canyons, deep narrow valleys carved into the seabed that can reach back to the shoreline and act as pathways for water and sediments, sometimes receiving direct input from river mouths, which also contribute to the formation of submarine fans. Additionally, seamounts underwater volcanic mountains form over hotspots, disrupt the otherwise flat ocean floor. Some remain submerged while others rise above the surface as volcanic islands. And there is unstable slopes often trigger massive submarine landslide involving large volumes of materials. Next is we will talk about the depositional processes in deep ocean, where the deposition of most plastic materials in deep seas occurs via mass flow processes, primarily the debris flows and turbidity currents. These processes exist on a spectrum with flows exhibiting intermediate characteristics. Yan. These are the depositional processes in deep seas. First is the debris flow deposits, turbidites, um, high and low efficiency systems, and the initiation of mass flows. The first one is the debris flow deposit. The debris flow deposit form when sediments reach poorly sorted materials from the continental shelf or slope is remobilized and flows downslope onto the basin plain, often mixing with seawater which causes dilution and sometimes transition, transitions the flow into a turbidity current. These deposits typically show a gradation from coarse materials at the base to finer sediments at the top, reflecting how the upper part of the flow becomes diluted by water interaction. The large-scale debris flows, such as those documented of Northwest Africa, for example, it creates thick, extensive sediments layers known as megabeds, and studying this deposit reveals important information about sediment transport, slope stability, the geological history of deep ocean basins, and the potential underwater geohazards. The second one is the turbidites. The turbidites are gravity-driven underwater flows of sediment and water that transport mixtures of mud, sand, and gravel from shallow areas to deep marine basins, forming deposits that vary widely in thickness and sediment concentration. These flows, which can move at speeds up to 100 kilometers per hour, as evidenced by events like the 1929 Newfoundland earthquake, creates characteristic sedimentary layers and play a crucial role in shaping deep sea sedimentary environments by distributing large volumes of materials over extensive distances. Next is the high and low efficiency systems. The deep marine depositional systems vary in efficiency based on how far sandy sediments are being transported or transported. The low efficiency system moves sediments only 10 of kilometers onto the basin plain and deposits in them near the basin edge, while high efficiency systems aided by high volume flows and finds that increased flow density carry the sediments over hundreds of kilometers farther offshore. In high efficiency systems, a sediment bypass zone near the basin margin prevents deposition, causing erosion or scarring of the seafloor, which can affect sediment distribution and help scientists understand sediment transport dynamics in deep marine environments. And last is the initiation of mass flows. Since turbidity currents and mass flows are triggered when an event like an earthquake, strong storm, waves, or excessive sediment buildup destabilize sediments on a continental shelf, it causing them to mix with water and move downward under gravity. Um, this often occurs near delta fronts where high river discharge supplies abundant sediment, generating dense, fast-moving currents that transport sediment from river mouth across the shelf and down into the deeper basins. So the depositional processes in deep seas are debris flow deposits, turbidites, high and low efficiency systems, and last is the initiation of mass flows.
We have here the depositional setting. Continental slope. The continental slope is the deep descent that begins at the outer edge of the continental shelf, known as the shelf break. It acts as the primary gateway between the shallow marine environments and the deep sea. This region is heavily incised by submarine canyons, which serve as the main pipelines, funneling vast amounts of sediment from the shelf down to the ocean depths through the powerful flows like turbidity currents. The continental slope is best described as the steep underwater cliff that marks the true edge of the continent. It begins where the relatively shallow, flat continental shelf suddenly drops off. This slope is curved by deep submarine canyons, which acts like giant pipelines, funneling vast amounts of sediment from the continent down into the deepest parts of the ocean. Next is continental rise, found at the base of the continental slope, primarily in geological, quite passive margins. The continental rise is a broad, gentle apron of accumulated sediment. It is formed from the successive deposit of sediment that spill out from the mouths of submarine canyons and spread across the seafloor, building up extensive features known as submarine fans. This the rise of the rise is characterized by its smooth, low-angle topography. At the bottom of the steep continental slope, we find the continental rise. This is a wide, gently sloping area made of accumulated sediments. It's formed over millions of years as sand and mud carried down the submarine canyons, spread out and settle on the seafloor. Think of it as a giant, soft apron of sediment that smooths the transition from the steep slope to the deep ocean bottom. Deep Ocean Basin. The deep ocean basin constitutes the vast, deep floor of the ocean, far from any continental landmass. This environment includes immense, flat, abyssal plains covered in fine-grained sediment, as well as deep-sea trenches formed by tectonic plate subduction on active margins. The basin is also punctuated by major volcanic features like sea mounts and the globe-encircling mid-ocean ridge system, where new oceanic crust is formed. Beyond continental rise lies the deep ocean basin. This is the vast, deep floor of the open ocean, which includes incredibly flat abyssal plains covered in fine sediment. This area is also home to dramatic features like underwater volcanoes, cold sea mounts, and deep sea trenches, which are the deepest places on Earth. It is the largest and most mysterious habitat on our planet. Also, have you ever wondered how sanded mud from our continent end up on the deepest parts of the seafloor? We're going to explore the incredible natural delivery systems that transport sediment from land to sea. We'll look at four key transporters. First, we have sediment plumes, where continental shelves are narrow. River discharge can create freshwater plumes that carry fine mud and silt far out from the coast. These surface plumes can travel considerable distances, potentially up to 100 kilometers offshore, before the clay particles eventually clump together and settle out of the water column. When we say sediment plumes, these are created by rivers that carry fine mud and silt from the land. When these rivers reach the ocean, especially where the continental shelf is narrow, They discharge this sediment in a large, cloudy plume of fresh water. This plume can travel a remarkable distance, potentially up to 100 kilometers offshore, before the tiny clay particles finally clump together and settle down through the water column to the sea floor. Next, we have the wind transport. This is a crucial important global mechanism. Winds blowing over continents, especially desert regions, can pick up and carry immense quantities of fine dust and silt particles out to sea. These particles can remain suspended in the atmosphere for vast distance before finally settling out over the open ocean, hundreds of kilometers from shore. In fact, the text emphasizes that wind transport is likely the primary mechanism for delivering clay-sized silicic-plastic sediment to the most remote, distant parts of the deep ocean basin. This process creates extensive blankets of very fine sediment. And third, we have the ice rafting. During the ice age of the Pleistocene, when sea levels were low and large ice sheets covered continents, icebergs were dominant transporter of sediments. As glaciers grind over the land, they incorporate sediment of all sizes, from clay to large boulders. These glaciers calve into the ocean to form icebergs. They raft this sediment away. When the icebergs melt, they drop this unsorted debris onto the seafloor, creating that what is known as glacial marine sediment. While this process is less significant on global scale today, outside of glacial periods, it remains active on a more limited scale in the Arctic and Antarctic regions. The signature of this process is poorly sorted sediment containing distinctive, often angular and striated rocks called dropstone. And last, Nipilioid transport. This is a key process for moving sediment of the continental shelf. Storms and waves can resuspend fine sediment on the outer shelf, creating dense, cloudy layers of water near the seafloor known as nipilioid layers. These layers can then flow off the shelf and down the continental slope. Denser nipilioid flows travels along the bottom, while less dense suspensions can flow along density boundaries in the midwater before eventually settling. These flows are powerful and extensive, reported to travel hundreds of kilometers seaward and each depth of 6,000 meters or more. Deep bottom currents help maintain these layers by constantly resuspending sediment. When we say Nipelloid transport, it is a key process for moving sediment off the continental shelf. Storms and waves resuspend fine sediments on the seafloor, creating dense cloudy layers of water. Near the bottom, known as Nipelloid layers, these sediment-rich layers can then flow off the shelf and down the continental slope like underwater rivers. These flows are powerful and can travel hundreds of kilometers seaward, carrying sediment from the shallow shelves out into the deep ocean basin. Next, we have current in canyons. Tidal currents measured in submarine canyons at depth exceeding 1,000 meters may be capable of transporting silt and fine sand. Two types of currents have been detected: ordinary tidal currents that flow alternately up and down the valley, and occasionally surges of strong down current flow with velocities up to 100 centimeters per second, which Shepard 1979 interprets as low velocity turbidity currents. These currents probably help to winnow canyons deposits and keep them free from fine sediments. And contour currents, density differences in surface ocean water caused by temperature or salinity variations, create thermohaline circulation, forming deep water masses that flow along the ocean floor as bottom currents. These currents tend to flow parallel to depth contours and are called contour currents. Their movement is also affected by the Coriolis force. Contour currents are deep bottom hugging rivers of water that flow along the ocean floor. They are created by density differences in seawater known as thermohaline circulation, which causes dense water masses to sink and flow. These currents move parallel to the depth contour of the seafloor, and their path is influenced by the Coriolis effect. As they flow, they are powerful enough to redistribute fine sediments, creating large sediment drifts and shaping the deep sea environment. And we have here the pelagic rain. Calcareous and siliceous shelled planktonic organisms settle through the ocean water column to the seafloor upon death, a process called pelagic rain or pelagic settling. Their distribution is affected by nutrients and ocean currents. After settling, they may be retransported by turbidity or contour currents. These skeletal materials from extensive biogenic deposits or oozes on the modern ocean floor and are important contributors to ancient deep ocean sediments. For example, is chalk, radiolarian chert, and diatomite. Fine silicic plastic particles transported from and may settle with organic remains to form mixed biogenic and siliclastic sediments called hemipelagic deposits. When we say pelagic rain, it is the constant gentle settling of dead microscopic plankton shells from the sunlight surface waters down to the deep ocean floor. The distribution of these calcareous and siliceous shells is controlled by ocean nutrients and currents. After settling, these biological debris can form vast blankets of biogenic ooze, which over geological time becomes rocks like chalk and chert. When this rain mixes with fine silt and clay from the continents, it creates a mixed sediment known as hemipelagic deposits. And now we have turbidity currents and other mass transport processes. A variety of mass flow processes take place within the deep ocean. Catastrophic high-velocity turbidity currents generated on the shelf or upper slope are the most important mechanisms for transporting sands and gravels to deeper water through submarine channels. Their deposits form deep sea fans and contribute to building the continental rise. On active margins, turbidities are discharged into forearc basin or deep sea trenches. Down canyon, grain flow of beach sands and submarine debris. Flows may also be locally important. Debris flow may be transported or transformed downslope into turbidity currents. Other mass transport processes like creep, gliding, and slumping are responsible for large-scale transport of sediments on over-steepened slopes. Some slump masses can be up to 300 meters thick and 100-meter kilometer long. Sediment can also be transported off oceanic ridges and seamounts. These currents are primary mechanism for transporting coarse sediment from the continental shelf through submarine canyons into deep water. When they reach the base of the slope, they slow down and deposit their sediment, forming deep sea fans that help build the continental rise. Other mass transport processes like debris flows and large-scale slumping also play a key role in moving enormous volumes of sediment down over steepened slopes, sometimes in massive blocks hundreds of meters thick.
Alright, let's take a closer look at this slide on the composition of deep marine deposits. At first glance, it might look like a lot of text, but let me break it down for you. Deep in the ocean, the seafloor is covered with different kinds of sediment, like sand, mud, and small bits of rock. These are called deep marine deposits. Where does this stuff usually came from? Mostly from land, especially from areas near the edge of continents. Things like rivers, waves, and the underwater landslide help move this sediment down into the deep ocean. Now let's talk about submarine fans. These are huge, fan-shaped piles of sediment found on the deep ocean floor. They form when sediment flows under They form when sediment flows down underwater slopes, kind of like an avalanche, through turbidity currents or mass flows. These fans can be made of sand, mud, or gravel, often coming from rivers or nearby shelves. Submarine fans are some of the biggest features on the seafloor, spreading out for hundreds of kilometers. Under the topic of submarine fans, there are three important we need to understand. First is the architectural elements of submarine fan system. A submarine fan is not just a simple pile of sediment. It's made up of different parts, each formed by different flow processes in the deep sea. These parts are called architectural elements, and they help us understand how sediment is moved and deposited across the fan surface. First, there are channels and leaves. Channels carry fast underwater flows full of sand and gravel, while finer sediment spills over the sides to form leaves. Next, at the end of channels, the flow slows and spread out, creating depositional lobes, widespread areas where sediments build up in layers that get thicker and coarser toward the top. Finally, away from the channels and lobes, turbidite sheets form as thin, fine layers of sediment that cover large areas. These parts work together to build the submarine fan and helps us understand how sediment moves and settles in the deep ocean. Next is the submarine fan system that is made up of channels, lobes, and sediment layers that vary in grain size. There are types of submarine fan system. Submarine fans can have different mixes of sediment. Gravel-rich fans have lots of gravel and sand near the basin edges, changing to mud farther away. Sand-rich fans are mostly sandy with strong channels and loops, but quickly change to finer sand and mud when the flow stops. Mixed fans contain both sand and mud, getting muddier as you move away from the source. Finally, muddy fans are mostly made of mud with some sandy channels and thin sand layers farther out. Each type shows how sediment moves and settles in deep ocean. Lastly is the ancient submarine fan system. These are underwater sediment deposits that got pushed onto land, but they are often squished or changed over time. By looking at the things like marks left by flowing water, scientists can figure out which way the water moved and how these fans built up layered by the air. Now let's take a look at the slope aprons and the contourites. Slope aprons and contourites are both underwater sediment deposits found along continental slopes, but they are formed in different ways. Slope aprons happen when sediments slide or flow down the slope in events like landslide and turbidity currents, making messy layers with big rocks blocks. Countries, on the other hand, form slowly from steady bottom currents that flow along the slope, creating smoother layered deposits. Both involve sediment moving along the continental slope, but slope aprons come from sudden events while contourites form from contourite currents. Now, let's proceed to ocean sediments. Ocean sediments are materials that settle on the deep seafloor, coming from different sources and forming in different ways. Pelagic sediments form very slowly from very tiny sea creatures, wind-blown dust, and volcanic ash, creating deposits like red clays and soft calcium or silica-rich muds closer to land. Hemi Hemipelagic sediments mix these tiny remains with more rock particles from continents, so they build up faster than pelagic sediments. Another type is the chemogenic sediments, formed through chemical reactions on the ocean floor, producing minerals like manganese nodules near underwater volcanoes. The type and location of these sediments depend on factors such as distance from land, the water depth, and how many tiny sea creatures live in the area. To further discuss pelagic sediments, these are fine materials like clay, ash, and tiny sea creatures, remains that slowly settles in the open ocean, forming red clays and mudstones. Distribution of pelagic deposits. Pelagic sediments build up mostly far from land in deep oceans, below about 4,000 meters. Calcium carbonate shells dissolve and don't stay on the seafloor, and below 6,000 meters, silica shells dissolve too. Sometimes bits of shells get to deep areas fast before they dissolve. Hemipelagic deposits are ocean sediments made from a mix of fine material and marine particles. They can be mostly carbonate, land derived, or volcanic depending on their content. These sediments are carried into the ocean by currents and storms, settling slowly to form mudrocks similar to nearby continental soils. And lastly, chemogenic sediments. Chemogenic sediments form slowly on the ocean floor from chemical reactions, including minerals like manganese, nodules, and metal oxides. Hydrothermal deposits form when seawater flows through rock nears underwater, creating hot band cold black smokers that release iron minerals, and cooler white smokers that build chimneys from calcium and barium minerals. In deep ocean deposits from Mesozoic and Tertiary periods, tiny plankton-like foraminifers, coccoliths, and radiolarians are the most common fossils, and their types can show how deep the water was. Trace fossils like Zupicus and Neritz also point to deep sea environments, but can sometimes appear in shallow water with little food or weak movement.
And now we have principal kinds of modern deep sea sediments. Little agreement exists regarding the classification of deep sea sediments. Two broad classes are often mentioned, trigenous and pelagic, though these are difficult to define precisely. Trigenous deposits include gravel, sand, and mud, derived from land and transported by processes like turbidity currents and ice rafting. Pelagic deposits include clays, derived from land by slowly settling and pelagic biogenic remains. A third minor category is arctonous deepwater carbonates transported from the shelf. Now we have terregenous sediments. This category includes hemipelagic muds, turbidites, conchurates, glacial marine sediments, slump and slides, all composed mainly of siliclastic materials. Under terregenous sediments, we have hemipelagic muds, turbidates, conchurates, and slump and slides deposits. Hemipelagic muds. These are muddy deposits that contain more than 5% biogenic remains and a terregenous component of more than 40% silt. There are deposits under very low current velocities and probably the principal sediment on continental slopes. And also, these are widely distributed on slopes of volcanic arcs. They range in color from gray to green to reddish brown, are composed of fine terregenous quartz, feldspar, micas, clay minerals, and/or volcanic sediments. And also, they are poorly laminated to massive and moderately to high bioturbated. There are deposits mainly from nepeloid layers and plumes. Hemipelagic muds are fine-grained sedimentary deposits characterized by a significant terregenous component and a biogenic content exceeding 5%. They accumulate under low energy conditions, primarily on continental slopes, through the gradual settling of particles from nepeloid layers. These deposits are typically poorly laminated, bioturbated and exhibit a range of colors due to their mixed composition of land-derived minerals and marine microfossils. Next is turbidites. They occur in the lower reaches of submarine canyons, deep sea channels, and most of deposit in broad, cone-shaped submarine fans, where canyons are closely spaced fans make quallies to build a continental rise. On active margins, they occur on the trench floor. Most are composed of sands, silty sands or gravelly sands, interbedded with pelagic clays, characterized by normal size, grading, and possible boma sequences. Soil markings are common. Mud turbidites composed of normally graded silt and clay also occur. Turbidites are the sedimentary products of turbidity currents, which are sediment-laden, gravity-driven flows. They are deposited in deep water settings, such as submarine fans and basin plains. These deposits are identified by their characteristic normal, grading, and sedimentary structures, often described by the Boma sequence, which results from the waning energy of the flow depositing successively finer material, and also conchurates. Several different conchurate phases are recognized: muddy, silty, sandy, and gravel-rich. A composite phases model is illustrated, showing overall negative grading from muddy to sandy conchurates, followed by positive grading. Back to muddy conchurates, they are often bioturbated and can have sharp or gradational contacts. Transport and deposition by contour currents may be more important than previously believed due to the role of abyssal storms. Conchurates are sediments deposited significantly reworked by the persistent action of contour parallel bottom currents. These deposits can range from muddy to sandy and are often structured in sequence that crescent upward and then fine upward, reflecting variations in current velocity. They are frequently biturbated and are now recognized as a major deposit type due to the influence of energetic abyssal circulation events. Lastly, we have slump and slide deposits. This consists of previously sedimented deposits in place downslope by mass movement processes, resulting in fault, contorted, and chaotic bedding. They are common on continental slope with high deposition rates. Emplacement by mass transport processes appears to be the dominant sediment transport process on some modern lower continental slopes. Slump and slide deposits are the result of mass transport processes where semi-consolidated sediment fails and moves downslope as a coherent mass. These deposits are defined by their internal deformation, featuring structures such as contorted bedding, faults, and general chaotic fabric. They are common on slopes where sedimentation rates are high and slope stability is exceeding. Now we have pelagic sediments. Pelagic sediment is generally taken to mean sediment deposit far from land by slow settling of particles. Pelagic clays are siliciclastic muds containing clay minerals, zeolites, iron oxides, and wind-blown dust or ash. They are commonly red to red-brown and cover vast areas of the deeper parts of the ocean below about 4,500 meters. Pelagic sediments with significant biogenic remains are called oozes. Oozes with more than two-thirds biogenic components are calcareous oozes, which are dominated by foraminifers, or siliceous oozes. Calcareous oozes are widespread at depths shallower than about 4,500 meters. Siliceous oozes are abundant at high latitude and in some equatorial upwelling regions. Planktonic sediments on steep slopes may be retransported to adjacent basins. Pelagic sediments are defined as deposits accumulating in the open ocean, far from terrestrial influence, through the gradual settling of suspended particles. They are broadly categorized into two types: pelagic clays, which are silicic classic deposits dominated by clay minerals and wind-blown dust that accumulate in the deepest basin below the carbonated compensation depth, and biogenic oozes, which are sediments composed predominantly of calcareous or siliceous remains of microscopic plankton. The global distribution of these oozes is controlled by depth, productivity, and ocean chemistry, with calcareous oozes prevailing above the CCD and siliceous oozes dominating high productivity zones. When we call CCD, it's the carbonated compensation depth. And lastly, we have the chemical sediments. Chemical processes can modify sediments. Example is dissolution or form new sediment. Clay minerals, zeolites, ferromanganese crusts, and modules and phosphates are formed in minor amounts of autogenic chemical processes. When we say chemical sediments, these are formed primarily by inorganic precipitation or diagenetic alteration at the site of deposition, a process known as oneigenesis. This category includes deposition such as ferromanganese nodules and crusts, phosphorites, odigenic clay minerals, and zeolites. These sediments form through chemical reactions within the water column or at the sediment water interface, often resulting from the slow accumulation of dissolved constituents in the deep ocean, making them distinct from detrital or biogenic sediments. And that's all, everyone. Thank you for watching and listening to us.